Hello boys and girls, welcome to something I have stumbled upon on the Star Citizen forums, a slower speed of light. This is not exactly a game, it's a kind of a game, but being a computer game is not its main purpose. The main purpose of this creation is to simulate what would it look like if you would travel at speeds which are close to the speed of light. I don't know whether you have ever had read anything about the theory of relativity and relativistic movements, but we had this at school in the physics classes, and I always wished to see what it would actually look like. We knew that there is this time dilation and red shift and blue shift of light waves, and that when you travel or if an object is moving at speeds close to the speed of light, it's kind of stretched and its changing shape and stuff like that. So I always wanted to see it and this game actually simulates it. It was written by a few guys at the MIT just for the sake of displaying this. So if we look at the credits, MIT Game Lab. So this was actually written by scientists who programmed it to their best knowledge of the theory of relativity. And options, what kind of options do we have? Volume, I think that's okay. Credits. Let's play it. Let's give it. It has a game-like intro. We'll go through it. Once upon a time, in a quiet village, there was a little child. Sadly, the little child fell into a death's icy grip far too soon. The little child's spirit began the journey to become one with light. But the speed of light was too fast for the small and clumsy little spirit. Luckily, the spirit world is full of magical orbs that slow down light. Collect orbs to slow down light to walking speed so you can finally move on. Alright, so it is not like we would be moving faster and faster until we move as fast as light, but we slow down the speed of light. But it's the same relatively seen, whether the light moves slower or we move faster. This shows us how many orbs we have collected, and here we compare our speed to the speed of light. And there is this little spectrum of visible light. As light gets slower, you will start to see beyond what humans can typically see. That's correct, because light getting slower, or you getting almost as fast as light, causes this red shift or the blue shift of wavelengths, and then you should be able to see this spectrum, this visible spectrum, moving towards the infrared or the ultraviolet corner of the frequency spectrum. You've certainly experienced this with sound waves. It's a good way a good analogy is the sound waves. You have certainly noticed when a car with a siren is passing you, that when the car approaches you, you hear, I don't know, a siren tone or two tones alternating, and you hear them slightly higher than they are actually produced. And when the car has passed and is getting away from you, these tones get lower, somewhat lower, because because why? It's not because sound waves are propagating through the air, or that they are traveling at the sound speed of sound. But if the car which emits them is moving, it doesn't make them faster. They still come to you at the speed of sound, but the to explain, the waves are somehow stuffed or compressed if the car is closing at you, and they are stretched if the car gets further from you. So that changes, it kind of modifies the wavelength, and the same happens with light. So you see the light a bit more reddish or bluish, depending on whether you're closing or getting away from the light source. Moving is pretty obvious, looking around and options. Okay, so loading, here we go. And here we are. Strange land now, but that's okay. We are a spirit trying to get to the light, and these are these orbs. So as we can see, we are now traveling in the right lower corner. We see at which speed we are traveling. It's our moving speed, and our moving speed will be constant through all the game. What will change is the speed of light. And it's strange that we already see a red shift and a blue shift. When I am approaching these houses, I see it all more bluish, and when I go away from them, I see them move to the red. And I wonder why this visible light spectrum is getting broader and narrower. Actually, it's getting broader. Always when I approach, and when I go away it's broader. But I see it more like red. Oh, maybe just the... I understand. I understand. It's not... If the light waves were static, of course they are static. So we perceive these slightly infrared waves as red because we are moving so fast that they actually shift towards the red and become perceivable for us. So you already see the colors changing, and now as we collect the orbs, you see that the pointer for the speed of light soon should start coming closer to us. We've collected 7 orbs so far, and basically nothing has changed. It's still too little a change for anything to become noticeable. If you have ever seen any graphs of these curves and this Einstein's equation about calculating the wavelength or the light, you see that it's really not linear. It's not like when you're traveling at 20% speed of light, everything becomes 20% more like when you are almost at the speed of light. So we have now collected 21 orbs, and the arrow showing the speed of light only slightly changed, but it is changing more and more, and you can see that the red shift is becoming much more visible, and the blue shift as we move toward an object. Red shift, yes. So the balls change their colors. It's much more perceivable now. But it's not only the color shift which is part of traveling at light speeds. Something which I couldn't imagine is an effect called lensing. We'll get to it once we will travel faster. So we are now about at the half speed of light now, 50%. So the blue shift is very apparent, and the red shift is it's currently changing the bluish color to the green spectrum. So parts which are in the visible light, in the blue part, they shift to the green. As I get away from these people and this village, it'll all turn green. And I think something like lensing is already becoming apparent. You see the picture already deforming slightly. Like when I start running towards these mushrooms, they it is like your lens through which you are looking in a camera changes, and this is getting so when I'm moving away from these mushrooms, it's like looking at it through a telescopic lens. Yeah, it flattens the depth, the perceived depth flattens, and when I'm closing at it, it's like looking at it through a wide lens. Yeah, so the field of view gets wider when I start moving towards it, like, and when I move away, the field of view narrows down. Wonderful. So it's already noticeable, this lensing effect. It is already noticeable. Let's see whether we can sneak through here. Yes. And now the things will change more rapidly. We will notice yet. The color shift is very stark now. We go all the way down to infrared. I don't understand why we can see so much of the infrared waves and so little of the ultraviolet. But maybe it's because these shifts also aren't linear. We can see all the way down to all of the infrared waves, so the color shift is really, when I move away, everything changes to red, and even beyond red to black. When I go away from that, you see a black, didn't you? Black thing. And now why is it when I move towards it, why does it change to red? It's strange. Why do I see the red sky there? It's something I don't understand. So somebody who is more familiar with the relativity theory and traveling at light speeds can please explain, why do I see that sky getting red when I move towards it? It should be ultraviolet. Can't explain that. Oh, it's black. Oh, and already becomes apparent when I strafe, when I move sideways, the side towards which I move has a blue shift, and when I move the other side, when I move away from, is a red shift. So now I will move to the left, and you will see that the left part of the screen will become more bluish, and the right part will shift to the red and greens. Yes, so here you see it. And I'm still traveling at the same speed. It's just the speed of light which gets slower, and in relation to me, of course, or the relative speed of me and light is that I'm almost traveling with the speed of light now. So we are at 80% now here, 81, 82. Ooh. Oh, this is getting very, very color shifted now. And the lensing effect, the widening and narrowing of the field of view becomes very apparent. So look, when I've moved away from, now I'm moving towards them. When I move away from them, it'll all shift to the infrared or even sub-infrared into the dark black. And also you will see that the field of view narrows down. Yeah, that these mushrooms in front of there, they will fill more of the view. They should spread out. Yes. As I'm moving away, they start getting smaller again. And when I move towards them, they get first smaller, because it's like I'm looking through a wide lens. Wonderful. So this is the lensing, and moving at the sides has this. And you see this gate is like, it feels like it's changing shape. It's walking through the gate now. 93, 94% speed of light. 95. I'll stop at 99 to play with it a bit more, because what happens when we have 100% is that the color shift won't be there anymore. The game will be accomplished. So let's see, I'm now at 99. So moving sideways causes one part of the screen being black, being so much below infrared that I can no longer see it. Oh, and And I wonder, why is it that I see this gate? It's probably the lensing effect. The lens distorts things around us. Yeah, it's amazing. So let's pick up the. Now let's walk around a bit more. So ultraviolet. I don't understand why we don't get all the way up to the ultraviolet thing. So now when we are almost at speed of light, I think when we are getting away from an object, it should almost look like we are standing there, because why can we see this fence? We can see this fence because it reflects the light beams, and the light beams are traveling into our eyes from this fence. So as the light beams travel, they travel at speed of light. Now when we move away from this fence almost at speed of light, the light beams coming from the fence will have trouble, or will need a long time before they reach our eyes. So we hardly notice that we are actually moving away from the fence. Is it? Yeah. Well, it's so black that I can't even see it. We must pick another object. Let's pick this mushroom, maybe. Pick this mushroom. As we travel away from it, it looks like we aren't traveling away from it at all. Only when I brake and when I stop moving, the light has enough time to come into our eyes and show us how far we've got away from these mushrooms. So now traveling away, and now stopping. And as we stopped, it showed us how far we've got from these mushrooms. The same thing as we are approaching them, I think. Hey, wait. As we approach them. No, actually, as we approach them, we should see the approach immediately. I can't explain it fully. I'm not as good in theory of relativity. I don't see why we don't see us approaching these mushrooms immediately. Probably again because of the lensing, because of the field of view got so wide that it shows some distance, although the distance is not really there. So let's pick up the 100th ball. All orbs collected. So now we don't see the color shift anymore, but we see the lensing. And the problem now is, we'll see how it's bending, that you can almost not see where you are moving. Let's move to that gate, and you think you are so far away, but we are actually through the gate. Let's move through that other gate. You think you're far, and now and it's this white gate we have to enter when for the game to finish, but I don't want to do it. I still want to experiment a bit here. Oh, it gets so hard to navigate. This is incredible. So now, when moving away from the objects, we shouldn't see anything moving. Yes, You see? That's how far I could get until I collided with this fence. And I got all the way from those mushrooms there. And we have stayed. We didn't see us moving away because the light reflected from these mushrooms couldn't reach our eyes, because we are moving exactly at the same speed as the light is trying to reach us. So we think we are still standing here, and all that lensing effect we see around, but we perceive that our destination to these mushrooms hasn't changed until we slow down at the fence behind us, and the light actually catches up with us and shows us how far we've got. Yeah? We don't see how far away we are moving until I collided with the fence. It's amazing. Let's see. Let's try this. Let's try to get away from this place. Yeah, you don't see us moving. All right, let's end this. And it's nice to see how they are bending over. Can't really explain that bending. That bending is probably due to the lensing that we see them like bent like this. But okay, let's pass through it. Move away, people. I've made it somehow. Okay, maybe I missed it a bit, but I've made it into the gate. And that's the end. So you see, this is not really a game like you would have fun playing, but as a physical or a relativistic experiment, it is very nice, and I like it very much, because it showed me how does it feel to travel at light speeds or speeds at relativistic speeds. Now you can read the summary. What happened? Oh, what's this? I don't know what that. I can't really read that. What happened? So let's read it. Make everything as simple as possible, but not simpler. Albert Einstein. In a slower speed of light, the speed of light slows down with every orb you pick up. I've explained that. It is impossible for you to reach the speed of light, but certain relativistic effects become more visible as you get very close. We've seen that. First long time nothing really perceivable happened until we've got about a third of speed of light or half speed of light, and then things around us changed quicker and quicker. Relativistic Doppler effect. That's that sound wave from the siren passing you, that you hear it higher and lower than it actually is, and this red shift, blue shift Doppler effect. It's scientist Doppler described it. Light behaves like a wave, and different wavelengths appear as different colors. As you and other objects move around, the wavelength of light changes, appearing redder or bluer to your eyes. Yes, I knew that much. Some light becomes infrared or ultraviolet, which your eyes cannot usually see. And other invisible sources of light will become visible. Yes, that's right. So, when I'm moving away from something, it has a red shift, it's shifted to the red. So if I'm moving away from something which emits ultraviolet light, which is not perceivable to me, the red shift causes it to shift into the visible spectrum, and so I can perceive it. So it's like my perceivable spectrum widens into the ultraviolet space. Then I see heat. Infrared becomes visible. when infrared becomes visible when we approach things, and ultraviolet becomes visible when we move away from things. Searchlight effect. Moving left, the objects on the left are brighter than the objects on the right. Brighter, really? Why? Light also behaves like a stream of particles called photons. When you run towards a stream of photons, more photons will hit you and the object becomes brighter. Ah, that's why we saw those black areas, because the amount of photons hitting our eyes was so little, so small, that it felt like darkness. Ah, that explains things, of course. Ah, guys, it's too bright, and the photons hitting the face. Yes, yes indeed. Yes, I didn't think about that. Searchlight effect. And special relativity. Light always moves at the same speed, so the speed of light is constant, then the distances and times in the world around you have to warp. Your time is different from the time in the world. It's called time dilation. Yeah, I don't understand that much of it. And your distances are different from the distances of the world. It's the Lorentz transformation. I should have paid more attention in the physics classes, because we've had that Lorentz transformation, or at least we've touched upon these topics. We didn't really calculate any of it, but we've talked about it. Why is, when I move at speed of light, so if you is constant, then distances and times in the world around you have to warp. That's maybe that's the thing, as I showed you at the end, right? As we were moving away from the fence or from a gate or from the mushrooms at light speed, it didn't appear like we are moving at all, because for us, we've seen us standing in the very same place as before, because the light beams coming from these objects to us haven't reached us, because we were moving away as quick as they. You have to be much closer to the speed of light to notice the more dramatic effects of Lorentz transformation compared to the... Yeah, so back to the first paragraph. So until we have stopped or decelerated below light speed, we then saw the light coming, and then we could observe where we actually stand. So it felt like warping. We were moving from a place, but it felt like we are still at that place, and once we've decelerated, it felt like we are not teleporting, but we are suddenly in a different place. So maybe that was like warping. But still, if somebody can explain it better or correct me, I'm not really sure at this. Anyway, in the next paragraph, you have to be much closer to the speed of light to notice the more dramatic effects of Lorentz transformation. The more dramatic effects of Lorentz transformation compared to the Doppler and searchlight effects. So searchlight was, as you move, you see more photons, move away, less photons. At the end of the game, the Doppler and searchlight effects are removed to make Lorentz transformation easier for you to see. And the Lorentz transformation is exactly this bending as you move around objects. Yeah, as they are moving into this gate. So it's probably related with this. So for you, it feels like this warping probably doesn't feel like you're moving, but as if your body is stretching. So we stood at the mushrooms and it was like our body is stretched to the place where the fence stopped us, and then it was de-stretched, or it was compressed again to our normally body size, so we saw our things around us. So that would explain this changing shape of things moving at light speeds. What I've read about the relativity. I think that's it. But how can time and space stretch? It seems so unreal. Yeah, but it's science. It's all explainable. It is like you don't move. At speeds of light, you don't move. You stretch from one place to another, and basically warp by it when you then decelerate. Maybe it's like that. Correct me if I'm wrong, if you are studying these subjects, but I think it's like that. And runtime effect, what was that? I didn't notice that. Normally, light is extremely fast, but it still takes time for photons to reach your eyes. When you look at anything, you are actually observing incoming light from some time in the past years. The farther you look into space, the further you look into history. This is easily noticeable when you look at objects moving relative to yourself. Objects normally beyond your field of view can become visible when you move near speed of light, as you see them as they were in the past. No, I can't follow. Of course, looking at the stars, it is common knowledge that you can see stars which are no longer there. If you're looking at star, I don't know, 7 million light years away from us, you see the star, but if the star erupts or disappears or whatever, you will see the light for 7 more million years, and you won't notice that the star is not there because it takes so long for the light to travel to us. But I can't get this with the field of view. This is easily noticeable when you look at objects moving relative to yourself. Objects normally beyond your field of view can become visible when you move near the speed of light, and as you see them as they were in the past. No. Lincoln's been shot, says the photon. Photon, for something so bright. You are too. You sure are slow. Maybe they don't mean the field of view like. The amount of how wide around you see, but how deep into, how far in front of you can see. But this would also always mean that to travel into the past, you would be traveling at speeds greater than light. Yeah, if I would be in empty space between Earth and a star, and I would travel away from the star towards the Earth, and I would travel at speeds greater than light, I would actually catch up with the photons which are long past me, which have long passed me, and I would see the time moving, the time going backwards. I can understand that, but that would involve moving faster than light, and we were not moving faster than light. There is yet a game simulation to write. How would it look like if you move faster than light? Can't follow this really. It's not really apparent how how when I move near the speed of light, I can see how things were in the past. In my understanding, I can only see that if I move faster than light. But again, correct me if I'm wrong, if I have some misunderstandings here. So acknowledgements, yes, all these smart people have programmed it. Einstein has invented it or described it. And relativity visualization. Okay. So that's it. That's the speed game, a slower speed of light. All comments explaining the phenomenons I couldn't grasp are welcome, and of course feel free to try it out yourself and play with it a bit. Thanks for watching.